we will be moving to our next speaker, Yuta Nakajima from JAXA. Yuta has a very good experience now with ontological modeling. He visited JPL for a year, and we worked closely together. And now that he's back to Japan, he is spreading the word over there. So we will hear from Yuta how ontological modeling is being used at JAXA.
Thank you, Margaret. Thank you, Margaret, for your. Margaret, I'm Yuta from JAXA, and currently I am a flight project systems engineer of ETS-9 project. It's a 5-ton class big satellite. And also, I am a methodologist at Systems Technology Unit in JAXA, which is a concept design shop at JAXA. And as Margaret introduced me, that I am a former visiting researcher at US 390K. And I learned a lot about OpenCSR, OML, and MBAC from fantastic mentors like Dave, Margaret, and Nick, and Steve. And what I learned at JPL is really valuable to JAXA digital engineering. So today I will show you how JAXA's concept study team applied OpenCSR, especially focusing on integrating semantic and analytical modeling. So JAXA's concept design shop, we are working on the mission formulation and system architecting using MBAC. And why OpenCSR and digital engineering? In concept design shop, we have two styles of work. First is agility-focused study called 60-day studies. So multiple domain engineer work together and explore mission concept and feasible solution through iterative cycle of study in a short period. Typically 6 days study. And workflow heavily rely on manual communication and analog information exchange. So we like spreadsheets and PowerPoint a lot. A system model isn't used because the study cycle is faster than building a system model in this stage. In this work style, we improve design process by carefully designing the methodology aligned with the actual study workflow. OML and automation add agility and rigor. The second work style is rigor concept studies. Dedicated team defines system specification for manufacturers after MDR. System models are actively used in this phase, but manual consistency checks cause errors, especially with larger team or complex models. Automation of model queries and analysis is limited. In this work style, strong validation and reasoning capability with OML and AutoDL reasoner improve the quality of system modeling activities. And here's a specific business question in a 6-day study of very low altitude imaging missions. The team continued to do analysis through the study cycle to find the balance between how much power your spacecraft consumes and how much solar panel and battery you are going to load it with. All of that need to meet the orbital trajectory and also observation requirements. We need to perform power budget analysis and orbit spacecraft configurations and operational scenarios are related in that. You are always trying to put larger batteries and solar panels as you can onto the spacecraft, and that depends on how much dry mass there is and operational scenario, such as when and how long should we perform observation operation in one orbit, or when and how many times should we perform data downlink and thruster firing. When using electrical propulsion system, thruster needs preheating before firing. And here's a challenge of our workflow. The way it usually happens is there is a whole separate process where different set of people have to go in and look at the operational scenario and sizing of components. In the left side of this slide, gathering and exchange of information for design analysis is human-oriented. In the right side, input and output of data to and from 3 analysis tool is done manually. Meanwhile, laser frequency used work patterns and products exist, such as parameter table or mass equipment list or power equipment list and timeline. So to solve these challenges, we made 2 solutions. The first one is we improve information exchange workflow of system configuration and mail pair. The user uses spreadsheet as a data input interface. Scripts of model generation and mass and power rollup calculation automate tedious processes. The update of a spreadsheet triggers a CI/CD pipeline to automatically perform model generation, model query, and rollup calculation, and also report generation. So we use OML Vision as a workflow orchestration platform. User inputs selected component with property of mass, component, power modes, and power by using spreadsheet. Then script automatically generate OML descriptions. Here we can see mail using OML Vision tabular views. For rollup calculations, we use Sparkle group by operation to calculate total mass grouped by the work package hierarchies. And here's a vocabulary for configuration and mail. So we use a work package viewpoint to aggregate the total mass of supplying component of authorship such as subsystem like AOCS or power subsystem. And concept of project work package and mission component are coming from JPL IMC ontology, and which is a foundation of our modeling. And we also built a prototype of power equipment list that generates power aggregation table for each operational mode. So since the calculation is simple, we also use the Sparkle code for aggregation. And here the vocabulary of power mode and pair. We implemented the methodology to aggregate power consumption for each operation mode through the relationship between system level and hardware level operational modes. And second solution is automation of power budget analysis workflow. So we automated the data exchange and analysis workflow between 3 analysis tools, orbital analysis and operational scenario generation and power budget analysis. Using power aggregation results described before, once the user set up an operational scenario, the workflow automatically runs trip analysis tool and deploy the result as a dashboard. So we divided our workflow for 4 stages, so build model and analysis and reporting and reviewing. Yeah, reviewing is a part of human-oriented part. But this process is very important to include the reviewing processes because people doesn't want to change the model intentionally. So we need to carefully review the analysis result and feedback the result into the model. And here's what our dashboard looks like. In this analysis result, these 2 peaks show the thrust firing. And it looks like a DOD, so maximum DOD exceeds the criteria or requirements. In this case, a systems engineer wants to improve power balance by stopping the firing in the shadow. So she changed the operational scenario using the spreadsheet like this. And commit the change, then pipeline run the analysis. So we use a previewed Docker image in the CI/CD pipeline, eliminated the bottleneck of R package and the Python installation, resulting in a 5 times faster workflow. And finally, we got an updated result like this. So all of the tedious process for the systems engineer is hide in the CI/CD processes. As a backend, we use OML Vision with executable notebook, such as Cloud Notebook and Jupyter Notebook. In this case, we use Cloud Notebook with our language for our scripts. Jupyter Notebook is also an option. And what is the role of the descriptive model in the analysis workflow? So a descriptive model tells the simulation workflow to configure the simulation scenario. In this case, we extract the graph of target system decomposition for the power rollup and state variables for simulations. And here the vocabulary for analysis workflow, analysis cases, and the parameters. We define a concept of simulation scenario and state variable to manage analysis case in parameters. Previous Steve comment say that I think that we need to define the more precise vocabulary to distinguish what the state variable and what parameter is. But in this workflow, we just use state variables. And these state variables manage analysis case and parameters. We also extend the IMC vocabulary, project vocabulary to describe the workflow. But the workflow part is still have some challenges because when we define the workflow in OML, we need to, we cannot automatically generate the script. So we just define the workflow to clarify what the task is and what the relationship between three analysis tool is. But the actual script generation is human-based. And so what the value of our workflow? So one of the value is automation. One of the value of automation is capability to expand the design exploration space. So we can run continuous analysis combining operational scenario for 8 orbital periods, which was difficult in the previous manual workflow. Analyzing 8 orbital revolution requires 17 rounds of analysis tools. And automation of workflow open a new door to design exploration processes, such as the balance between increasing resources and elaborating operational plannings. And another interesting value we found is agile design sprint. Here's the actual design sprint of 1 day. System engineer set up scenario and run fast analysis and review it, then revise scenario. Same cycle happened 8 cycle within 4 hours. And automation eliminate manual bottleneck, turning days of work into hours. At the same time, methodologists accompany the systems engineer to continuously improve the workflow and tooling. And as a next step, we want to map analysis result to the requirement. So requirement, for example, requirements say that the maximum depth of discharge of the battery shall not exceed 60%. We can also add the scale property to manage a value of requirement of 60% like this. Then we evaluated our analysis result here like this. So maximum DOD is less than 60%, which is a requirement. So how can we realize requirement validation rule? One way to do this is using Spark query as shown in this slide. So max DOD requirement has max DOD value. which is supposed to be less than 60% in this case. And max DOD requirement also specify assume initial state value that is updated by the simulation result. Comparing the two values, we can validate the requirement. So like this. So when analysis results say 50%, validation rule said it's okay, but analysis result is 80%. Analysis validation rule says not valid. And also another interesting way is using SWOBI less than built-in vocabulary to validate the analysis result. We just explained how the rule works. In this approach, we can embed the requirement validation as a rule in vocabulary. And it is interesting to see that SysML-v2 provides a mechanism to embed attributes and constraints in requirement and perform validation of requirement based on rules. So I think that our OML also support this kind of analysis for requirement validation. And next, so I will show you third solution, SysML model validation using OpenCSR for rigor concept studies. Here's a problem. So the current SysML modeling process has difficulty to validate the model we built consistent with our intent of the designed meta model. In our approach, we validate this model with respect to the meta model by leveraging the powerful consistency checking and inference capability of OML and OpenCSR. We built a mapping of our SysML meta model to OML vocabulary. Then, using the vocabulary, we transform SysML model to OML descriptions. Finally, reasoner check the consistency. So here's a simple example. So requirement A derives requirement B, and block B satisfies requirement A, and requirement B derives requirement A, and requirement B also derives requirement B. Is this semantically rigorous? In OML, reasoner detect inconsistency using vocabulary. In the process of ontology development, we can add information for the DL reasoner to check the constraint of nodes and edge using DL flag. For example, if irreflexible is no node linked to itself, asymmetric is no link is bidirectional. Reasoner check model consistency based on the vocabulary designed in OML. And we map the SysML meta model into OML. Then we apply the reasoner to detect inconsistency using the reasoner. OML adds capability to figure in systems engineer with reasoner. We can detect these errors using asymmetric, irreflexible, and from-to definitions. And next idea is using power of inference. Here we have simple functional decomposition and related requirement definition. So there's a function A0 and A0 decompose A1 and A2, and at the same time, the requirement is mapped to the function. And we have function to requirement mapping with satisfied. Function has also hierarchy like this. And how do we relate between requirements? Requirement A0 and requirement A1, or requirement A1 and A2, or A0 to A2. As a design intent, the hierarchy of functions should match the hierarchy of requirements. So requirement A1, which is satisfied by the lower level function A1, should be connected to requirement A0, which is satisfied by the upper level function A0. And in OML, reasoner can add the edge using inference rules. Using inference rules, the machine, in this case, the reasoner automatically assigns relationships. In this case, inference rules is the parent-child relationship of requirement follow the function decomposition. So function A1 invokes function A1.1 and function A1.2, and requirement to A1 specify function A1, and requirement to A1.1 specify function A1.1, and requirement to A1.2 specify function A1.2. Thus, requirement A1.1 trace requirement A1, and requirement A1.2 trace requirement A1. We can describe this rule like this. Yeah, on the right side, we have a rule like inference rule. So this table shows our experiment on actual project. So there are 3 types of model validation checking, and we can use Reasoner or Spark query to realize the rule. Once we transform system graph into OML, OpenCSR and all Reasoner is powerful for automatic validations. Here's an example of inconsistency or usage of allocate to XFS design intent. In our SysML methodology, function is mapped to subsystem activity, and subsystem activity is allocated subsystem block. As a methodology, designer add this arrow from allocate function allocate to subsystem block. And subsystem activity also allocated to subsystem block. We can also add this arrow using inference rule. So there's a triangle relationship between function, subsystem activity, and block. So using this triangular relationship, these are automatically add this rule. When activity is derived from function allocated to a block, we infer that the function are allocated to the same block. Once you embed the inference rule, the validation query code is just 1 line, so it's very powerful and very short. Okay, so here's a summary of my presentation today. So rapid design iteration is the heart of early mission design. So our approach automates multi-domain power budget analysis workflow using OpenCSR to orchestrate semantic and analytical models. And we leverage OML Vision as a workbench integrated with cloud executable notebook. We introduced the idea of system model validation using OML and Reasoner also. And OpenCSR is a rigorous and agile digital engineering methodology that helps in the early phase of space mission study. So thank you for your attention.
Thank you so much, Yuta, for the inspiring presentation. Is there any question to Yuta from the audience? We have a question from Nicholas.
Yes, you mentioned a few slides ago, I think it was like around 12 or 13, something about scenarios. Before that. Yeah, okay, no, the next slide.
This one.
No, the next one. Yeah, the operation scenario here.
Yeah.
I'm sorry, like the previous slide.
Yeah.
Could you explain a bit more how you describe operation scenarios in your approach?
Okay, so we use power mode and relational. So we have a power mode ontology. So power mode defines a component power mode. So for example, Star Tracker has on and off mode, and thruster has an on mode or firing mode and preheat mode. So power mode describes the state of components. And we also have an aggregated power mode, which describes the system level of operational mode. So for example, there's a mission observation mode, imaging mode, and also data downlink mode, and thruster firing mode. So using this higher level of operational mode, these operational mode map to the each component power mode. So using this simple power mode ontology, we can aggregate the total consumption of spacecraft, total power consumption of spacecraft. So using this information, we specify the scenario, which is scenario is like allocating the time slot of one orbit. So, for example, we use mission observation power mode, mission observation mode from the start from 20% or to 20% of the one orbit to 70%. It's like 50% during the 50% during the one orbit, we perform the observation operations.